Hello there, welcome back to this video. Today we are going to talk about differential equations and connecting it to previous topics learned in AP Calculus, specifically topics in the differentiation units, because after all, a differential equation is a derivative. Alright, so let's go ahead and dive into this. Like I just said, a differential equation involves a derivative. So that's a very important idea to connect, that when they give you a differential equation, that's a slope. Now, since we have a derivative, we could be asked to do a few things involving derivatives, okay? This could include writing the equation of a tangent line, because we need two things, a point and a slope. Well, we have the slope. We could be asked to approximate a value using that tangent line. Usually this is one question that's fairly common. Number 3, we could be asked to find a second derivative. Okay, that will often include implicit differentiation. And then lastly, find or check for critical values of relative extrema. If I'm given a derivative, I can easily analyze if the function is increasing or decreasing there, and the second derivative would allow me to analyze concavity for maximums and minimums based upon that. Okay, so those are the 4 things that are most common. We'll see some other stuff kind of pop up here, but let's dive in and look at this differential equation. dy dx is equal to 4x over y. Let y equal f of x be the particular solution to the differential equation with the initial condition f of 1 equals -4. That's very important because when they give you this, they're giving you a point. 1, -4. They say write the equation for the line tangent to the graph of f at 1, -4 and use it to approximate f of 1.3. Okay, well, in order to write a tangent line, which I'll abbreviate as TL, you need 2 things. We need a point. Well, the good news is the point they gave us. It was 1, -4, so I have that there. Now, I do need the slope. Now, the slope is just going to be dy dx evaluated at this point, 1, -4. I'm just going to plug that in. So 4 times x, my x value is 1, divided by y, which is -4. So it looks like our slope is -1. Okay, so hey, I got a point, I got a slope. All right, now they say write the equation for the tangent line. So that's one thing that you have to go ahead and do. You have to do this to earn the point on the AP exam. Y minus -4, so y plus 4 equals -x minus 1. So there's my equation. Generally, writing the equation, that would be 1 point. And then now we'll go ahead and we'll approximate f of 1.3 by plugging this in. So -1.3 minus 1. Okay, and then I'm going to subtract 4. I just moved that 4 over, subtracted it on both sides. So this is approximately, because that's what we're doing. We're approximating. I like to always use that approximation symbol there. I don't know, I have not been a grader yet at the AP exam. Maybe one day I will find out if that makes a huge difference. -0.3 minus 4, that's going to be -4.3. There you go. Okay, that's approximating using the tangent line. So, a couple of things. Writing the tangent line, big idea. Big idea. Okay, and then approximating. All right, B. Find d squared y over dx squared in terms of x and y. Okay, so if I am going to go ahead and take a second derivative of this, I need to go ahead and use the product rule. And oftentimes differential equations are in fractional form. So I'm going to have to take the derivative of the numerator, which is 4, times the denominator, which is y, minus the derivative of the denominator, which will be dy dx, right? 1 times dy dx, the derivative of y, times the numerator, which is 4x, okay, all divided by the denominator squared, y squared. Okay, they want it in terms of y and x and y. So we had to just substitute back in dy dx. So this gives us 4y minus dy dx, which is 4x over y, times 4x over y squared. Now that's fine. I would advise my students to stop there, especially if this is a FRQ and you have to find the second derivative. But if this is multiple choice and you need to simplify, you may see it in a form where they get rid of this y right here. They just decide to multiply everything by y over y. Now what that does is this y, when we distribute, right? Don't forget you have to distribute to each term. This one cancels. We end up getting 4y squared minus 4x times 4x, which would just give us 16x squared, all divided by, and then we multiply in the denominator as well, and we get y cubed. Okay, so that would be another alternate form that you may see. C. Let y equal f of x be a particular solution to the differential equation with the initial condition f of 1 equals -4. Does f have a relative minimum, a relative maximum, or neither at x equals 1? Justify your answer. Well, think about this. In order to be a critical value, a relative min or a max, dy dx needs to be equal to 0. Okay? So critical value means, this is the first step, that y prime, right, dy dx is equal to 0. Okay, that just means your slope is 0, right? Now, I don't know if it's a max or a min, you know, concavity could come into play, it could be a saddle point, but that's the first step. So, didn't we find out right away up here? Didn't we use dy dx evaluated at 1, 4? We found that, and that was -1. So dy dx evaluated at 1, -4 equals -1, which is not 0. You could say so. F has neither a relative max or min. At x equals 1. Okay, so you could say f has neither, but because you have to include this part right here. You must include dy dx evaluated at 1, -4 equals -1, which is not 0. Okay, think about how would I show it if it was 0, how would I know if it was a relative minimum or a relative maximum? Well, didn't we just identify the second derivative? Doesn't the second derivative give us concavity? So you could always use that second derivative sometimes to see, hey, if it's concave up, then we know we have a minimum. If it's concave down, and you just use that second derivative to justify that. Okay. All right. Pretty sweet. Example number 2. This is the FRQ from AP Calc AB in 2010. I'm going to go ahead, I'm going to let you solve this one. I'm going to let you guys work on this. I'll show you the answers here in a second. Pause me, and then I'll do the answers in waves, okay? All right, hopefully you went ahead and tried this one. Part A, they want us to write the equation for a tangent line. Again, the point given is 1, 2. They gave us that, 1, 2. Now, I do need the slope. I do need my slope. So I'm going to take dy dx, I'm going to take that differential equation, and I'm going to evaluate it at that point, 1, 2. So we have 1 times 2 cubed, which looks like it's just going to be 8. So that equation, y minus 2, is equal to 8 times x minus 1. There you go. There's your equation of a tangent line. Okay? All right. B. If you haven't tried B yet, go ahead and try B. So B, I am going to approximate f of 1.1 by plugging it in here. So 8 times 1.1 minus 1, and I'm going to add 2. So this gives us 8 times 0.1 plus 2, which is equal to 2.8. Okay, so 2.8 is the approximation. All right, and then example C, or part C, in order to find the second derivative, we're going to have to do product rule. This one's product rule because they're multiplying. They're multiplying. So derivative of the first, which is just 1, okay, times the second, y cubed, plus derivative of the second, we have 3y squared dy dx, that's the derivative of that, times the first, which is x. And they want it in terms of x and y. So all of this would be y cubed plus 3xy squared times dy dx, that's this part, let me put it in a different color for you, is x y cubed. Whew. Okay, so if I wanted to clean this up, y cubed plus 3x squared y to the 5th. Okay, there you go. All right, hopefully we're doing well and cooking right along. Example number 3. Again, this is just very, very similar to what we've been doing. They say consider the differential equation dy dx equals x minus 1 over y. Let y equal f of x be the particular solution to the differential equation with f of 1 equaling 2. There's your point. Write the equation for a line tangent to the graph of y equals f of x at x equals 1. Okay, the point I am given is 1, 2, and then I need slope. So I'm going to take dy dx, and I'm going to evaluate at that point, 1, 2. So we plug this in, we get x, we get 1 minus 1, there we go, 0 over 2. So that's 0, slope is 0, okay? So if you have a slope of 0, isn't that a flat line? That's a horizontal tangent line, just flat. Okay, so y equals 2. If it goes through that y value, it should be 2. But I'll show you that using the same format that I've been doing. Y minus 2 is equal to 0. There's your slope times x minus 1. All of this is 0, isn't it? Y minus 2 equals 0. Here's your equation. Y equals 2. Okay, that's a cool one. Example 4. All right, now we're talking. Example 4. Here's where we go into context, and we have not x's and y's, but we have h's and t's. Remember, if you have a t in there, that's usually time. That's going to be an independent variable. And if you're ever confused, just think about where does the x normally go? Isn't it usually dy dx? So in this case, our dependent variable is h. Sometimes it'll represent like heat. This could be whatever the context is. Example 4. Consider the differential equation with a particular solution through h of -2 equals -1. Use the tangent line to the graph of h at t equals -2 to approximate h of -1.9. So again, I'm going to need a point, and they gave us the point -2, -1, and then I need slope. So I'm going to take dh dt, and I'm going to evaluate at this point -2, -1. So we'll plug this in, we get -2 plus 1 over -1 squared. This looks like -1 over 1. So slope's -1. Slope is -1. Okay. So I got that. Now I'm going to go ahead and just generate my equation. So y plus 1 is equal to -1, x plus 2. So that means h of -1.9 is approximately -1.9 plus 2 minus 1. So we have -0.1 minus 1, so -1.1. That's the approximation. Not too bad. Okay, B, another second derivative example here. Find d squared h over dt squared in terms of t and h. Okay, we've done this one before. So I'm just going to go ahead and take a second derivative. It looks like quotient rule. So derivative of, well, let me get my notation in here. Ignore me. You don't know me. D squared h over dt squared. So derivative of the top is going to be 1. We're taking it with respect to t. So 1 times the bottom times h squared minus derivative of the bottom 2h dh dt. All right. Took the derivative, 2h times the derivative of h, dh dt. Okay, times the derivative of the top now, t plus 1, all over the denominator squared, h squared squared. Okay, so we'll put this in terms of h and t. So we get h squared minus 2h t plus 1, and then I'm going to include dh dt here, okay, over h to the 4th. Again, like I said, you can go ahead, you can multiply, it looks here like you'd multiply top and bottom, everything by h squared. H to the 4th equals, I guess I could do it. Running out of room here. Okay, so this would be h to the 4th minus 2h times t plus 1 squared, right? If I multiply by h squared here, that's going to cancel. We get t plus 1 squared, and then multiply by h squared here, and h squared here. Over h to the 6th. Right? Multiplying variables, we're going to add those exponents. So there might be a multiple choice one that you would see. Okay, example 5. All right, example 5, I'm going to have you guys go ahead and try example 5, use it as a practice problem. Again, we are calculating the tangent line to the graph of this function r of t representing the population of rabbits to approximate the number of rabbits after 4 days. And then part B, finding the second derivative. Please, excuse me, please skip C. Skip C. At least in my curriculum, you have not been equipped yet in order to find a particular solution. We do that in the next video, the next lesson. So you can skip that. You can always come back if you love the bunny rabbits and you want to answer this question. We'll skip that. So right now, please pause the video and then go ahead and attempt A and B. See you in a second. Okay, hopefully you went ahead and tried these. The first thing that you need in order to get a tangent line is a point. So the point would be 0, 50. There's 50 rabbits at time t equals 0. The slope that's given, that's dr dt. So you go ahead and you evaluate at that, and that would give you 0, 50. So we plug this in and we get 1/6, 120 minus 50, the number of rabbits. That gives us 70 over 6. So there's your slope. So in order to approximate this, our equation, our tangent line, y is equal to 70 over 6 times x minus 0. Minus makes this a plus 50. So there's your equation, and if we want to approximate 4, if we're going to approximate 4, I guess r of 4 is approximately 70 over 6 times 4 plus 50, which gives us 280 over 6 plus 50. Okay, so I would go ahead and leave that. That's not a nice clean number. What do we get? approximately 46 rabbits, so approximately 96, 97, what does my paper say? 96.66666. Approximately 97 rabbits, if you want it contextual. Okay, and then part B, here we go. I'm going to go ahead and show you part B. So there you go. There is our second derivative. You take the derivative of the first, you should have got 1/6 times -1, that's the derivative of negative r, times the derivative of r dt. So we just substitute dr dt in here, and you should have gotten -136 times 120 minus r. Okay. All right, example 6. Here we go, example 6. These questions are actually pretty fun. I kind of like these problems. They say, consider the differential equation. Describe all the points in the xy plane for which y is not equal to 0, for which dy dx is equal to -1. So I want dy dx to be equal to -1. And sometimes you're like, okay, where do I go from there? Well, ask yourself, what is dy dx? Oh, that's x plus 2. So I'm going to say, okay, x plus 2 over 2y equals -1. Okay, how do I solve that? Well, I'll go ahead and multiply both sides by 2y, and we get x plus 2 is equal to -2y. Okay, and then I'll go ahead and isolate y. I'll divide both sides by -2, divide by -2, divide by -2. Okay, and we get y is equal to -1/2 x minus 1. Okay, so I have that example. So what does it all mean? What does it all mean? Well, we can say, they want a response here. So we'll say any point on the line y equals -1/2 x minus 1, except y not equal to 0, then dy dx is equal to -1. So we're just describing all the points in the xy plane for which the slope is equal to 1. So all the points are on this line, y equals -1/2 x minus 1. Okay, I'd like you to try B. B is very, very similar. So describe all the points in the xy plane where y is not equal to 0, for which dy dx is equal to 2. All right, hopefully you went ahead and solved this one. Dy dx is equal to 2. Well, all the points, if I go ahead and solve for where the slope is 2, we get y is equal to 1/4 x plus 1/2. Okay, so just using a similar template from before, at any point, y not equal to 0, y equals 1/4 x plus 1/2. Then dy dx is equal to 2. Okay, so at any point where y is not equal to 0, y is equal to this, then the slope will be equal to 2. Okay? All right, example 7. Example 7 and in turn 8. These ones are more critical thinking. These ones are kind of cool. Again, consider the differential equation. Describe all points in the xy plane, y not equal to 0, for which dy dx is equal to negative. Okay, so they're saying that dy dx is negative, less than 0. Well, dy dx is x minus 2 over y squared. That has to be negative, less than 0. And if you know anything about powers of 2, that makes the denominator always positive. Always positive. Y squared is greater than 0 for all points. For all points. Doesn't matter what y is, that will always be positive. Well, in order for this whole thing to be negative, this means that x minus 2 must be less than 0. Okay, so what does that mean? Well, if I go ahead and solve this, if I just add 2 to both sides, we get x must be less than 2. X must be less than 2. Okay, so we can say at any point where x is less than 2, dy dx is negative. Kind of fun looking at the structure. All right, B. Describe all the points in the xy plane, y not equal to 0, for which dy dx is positive. Okay, so now they want dy dx to be greater than 0. Well, again, since y squared is always positive, that means that x minus 2 must be greater than 0. Okay, so this just gives us x must be greater than 2. So at any point where x is greater than 2, dy dx is positive. That's it. That is it. Okay, example 8, I want you to pause, try this one, try example 8, and I'll go over it here in a moment. All right, similar structure for this one. If they want the derivative to be negative, x squared times 3 minus y, that's the differential. If that's going to be negative, well, notice x squared, that's always positive. That quantity is positive. So that means that 3 minus y has to be negative. So if we look at that relationship and then go ahead and solve for y, I'll subtract 3 on both sides. And then notice when we go ahead and multiply or divide by a negative, the inequality flips, right? So y is greater than 3. So we would say at any point where y is greater than 3, then dy dx is negative. All right, hey, that's going to do it for me. In this video, we went ahead and looked at possible applications of a differential equation. And in the next video, we'll talk about finding particular solutions. I got to run. I got to answer this phone. See you in the next one. Peace.